Imagine a cosmic lighthouse, spinning with such perfect regularity that it sweeps a beam of intense radio waves past Earth every 1.2 seconds with clockwork precision. This isn't science fiction. This is a pulsar, one of the universe's most extreme objects, a neutron star so dense that a teaspoon of its material would weigh billions of tons, spinning at impossible speeds while emitting beams of electromagnetic radiation from its magnetic poles. Astronomers have cataloged thousands of pulsars since their discovery in 1967, and they've become such reliable timekeepers that they're used for testing Einstein's general relativity and even for deep space navigation. But in early 2026, something changed. A pulsar designated PSRJ 2337+61, located approximately 10,000 light-years away in the constellation Cassiopeia, began exhibiting behavior that doesn't fit our models. The upgraded square-kilometer array, the world's most sensitive radio telescope network, which became fully operational in 2025, has been monitoring this object with unprecedented precision. What it's detecting is profoundly unsettling to astrophysicists. The signal is not only continuing, it's becoming stronger and more structured over time. This shouldn't happen. Pulsars are supposed to gradually slow down as they lose rotational energy. They're supposed to be predictable, well-understood objects. This one is doing something different, and the scientific community is scrambling to explain why. When you point a radio telescope at the sky, you don't just get clean signals. You get noise, lots of it. Cosmic microwave background radiation, emissions from distant galaxies, interference from Earth-based sources, and countless other radio sources create a chaotic soup of electromagnetic signals. Extracting meaningful data requires sophisticated signal processing, and that's where artificial intelligence has revolutionized modern astronomy. We're now using machine learning algorithms trained specifically to identify and isolate pulsar signals from background noise, with accuracy that human analysis could never achieve. When these AI systems were applied to PSRJ 2337+61, they revealed something extraordinary. The main pulse occurs every 1.2 seconds, as expected, but within each pulse, there are subpulses, smaller nested patterns occurring at microsecond intervals. This isn't entirely unprecedented. Some pulsars show subpulse structure. But the subpulses from this object aren't random. They exhibit mathematical relationships, specific timing ratios that repeat with statistical significance far beyond what chance would produce. Some researchers describe it as almost musical, with harmonic patterns that suggest underlying organization. Even more peculiar are the frequency shifts. When a pulsar rotates, the radio waves it emits should show predictable Doppler effects based on the star's rotation and any orbital motion if it's part of a binary system. But this pulsar's frequency shifts don't match the simple rotation model. They vary in ways that suggest either the rotation rate is changing, which would require an external energy source, or something about the emission mechanism itself is varying in a structured, non-random way. Neither explanation fits comfortably within standard neutron star physics. Here's where conventional astrophysics starts breaking down. Neutron stars are the remnants of massive stars that exploded as supernovas. They're born spinning rapidly, sometimes hundreds of times per second, but they inevitably slow down over time. The spinning magnetic field creates electromagnetic radiation, and that radiation carries away rotational energy. It's a one-way process. Pulsars spin down, they don't spin up. Except this one appears to be doing exactly that. Precise timing measurements over the past 6 months show that PSRJ 2337+61's rotation period is decreasing, meaning it's spinning faster, not slower. The acceleration is tiny, just a few nanoseconds per month, but it's statistically significant and consistent across multiple observation sessions. This suggests the pulsar is somehow gaining rotational energy. But from where? The possible explanations are all exotic. Perhaps it's accreting material from an unseen companion star, but there's no observational evidence of a binary system, and the accretion would produce X-ray emissions we're not detecting. Perhaps it's interacting with a dark matter cloud, though that's highly speculative and lacks supporting evidence. Perhaps there's some quantum mechanical process occurring in the neutron star's interior that we don't yet understand. Exotic physics involving quark matter or strange matter phase transitions. The timing precision also eliminates other conventional explanations. Some pulsars show apparent timing variations because they're being gravitationally lensed by a companion object, creating the illusion of changing pulse rates. But gravitational lensing produces specific, predictable patterns that don't match what we're observing. The signal variations are too structured, too mathematically precise, to be explained by simple orbital mechanics or gravitational effects. When confronted with an anomaly, scientists' first instinct is to check if it matches any known phenomenon. Comprehensive database searches have compared this signal against supernova remnant emissions, black hole accretion signatures, magnetar bursts, and every other cataloged high-energy astrophysical process. None match. The signal structure is unique in our current astronomical database. What's particularly intriguing and controversial is pattern analysis suggesting non-random information content. When you analyze truly random signals statistically, they produce certain distributions. Natural processes, even complex ones, create patterns that reflect underlying physical laws. But when information theorists apply algorithmic complexity analysis to the subpulse structure of PSRJ 2337+61, they find what appears to be higher-order organization. Some researchers, though definitely not all, argue the signal shows characteristics more similar to compressed data than to pure noise. This is where the scientific community divides sharply. One camp insists we're looking at a natural phenomenon we simply don't yet understand, exotic stellar physics that will eventually be explained by extensions to current theory. They point out that throughout history, unexplained astronomical observations eventually yielded to natural explanations. Pulsars themselves were initially jokingly called LGM signals for little green men, until the rotating neutron star model was confirmed. The other camp, smaller but growing, suggests we should seriously consider that we're detecting something genuinely anomalous. Not necessarily artificial, but perhaps representing physics so far outside our current understanding that it requires revolutionary new theoretical frameworks. So what are the implications? If this signal is natural but requires new physics to explain, it represents a major opportunity for advancement in our understanding of high-energy astrophysics, neutron star interiors, and perhaps even quantum gravity effects. New physics means new technology, new capabilities, and expanded understanding of the universe's fundamental rules. That's exciting enough on its own. But if, and this is still a very speculative if, the signal contains organized information of non-natural origin, the implications are obviously profound. It would represent the first confirmed detection of technological activity beyond Earth, fundamentally changing humanity's understanding of our place in the cosmos, and likely triggering a complete reevaluation of SETI methodology and astrobiology priorities. The next phase of observation is scheduled for next month, using coordinated observations from the Square Kilometer Array, the Very Large Array in New Mexico, and the upgraded Arecibo Substitute Facility. These observations will provide even higher signal-to-noise ratio data, potentially resolving whether the apparent acceleration is real or an artifact of observation techniques. Additional analysis will search for any periodicity in the subpulse patterns that might indicate encoding of information. Right now, PSRJ 2337+61 remains genuinely unexplained. It's a cosmic mystery being investigated with the full toolkit of modern astrophysics, and the answer, whatever it turns out to be, will expand our understanding of what's possible in the universe. Whether it's exotic natural physics or something more extraordinary, we're watching science in real time as it confronts the unknown.